Determine all composite integers, n greater than 1, that satisfy the following property. If d1, d2, 2, dk are all positive divisors of n in ascending order, then di divides di plus 1 plus di plus 2 for every I between 1 and k minus 2. This is problem 1 from the 64th International Mathematical Olympiad. We will need to find all the composite integers. When positive divisors are arranged in increasing order, each divisor must divide the sum of the next two divisors. Interestingly, 77% of IMO participants scored full marks on this problem, indicating that this problem was relatively easy by competition standards. We will start with a simple example by testing 6. The divisors of 6 are 1, 2, 3, and 6. Since 1 divides every integer, we start from the second divisor, which is 2. Here, 2 does not divide 3 plus 6, so 6 does not satisfy the condition. Now let's test 8. The divisors of 8 are 1, 2, 4, and 8. Starting with 2, we check that 2 divides 4 plus 8, so 8 satisfies the given condition. This is one trivial solution, but we need to find all such numbers. A composite integer can be expressed as the product of prime numbers. For example, 6 equals 2 times 3, and 8 equals 2 cubed. We will find the general solution for numbers like 8, which has only one prime factor, if we consider numbers like 16, 32, or 64. These are also powers of 2, and their divisors also are powers of 2. When arranged in ascending order, each divisor always divides a larger divisor, and thus divides the sum of the next two divisors. We can generalize the expression as p to the power k, where p is prime and k is a positive integer. The divisors will be 1, p, p square, p cube, and so on. Since every divisor is a power of p, each divisor divides the sum of the next two divisors. Thus, any composite integer that is a power of a single prime satisfies the given condition. Then we will consider a composite integer with more than one prime factor. Let's say there is a distinct prime, q, for a composite integer. Without loss of generality, assume q is larger than p to the k, where k is greater than 1. The divisors of such a number include terms like p to the power k minus 1, p to the k, and q. Since q is a distinct prime, p to the k minus 1 does not divide the sum of the next two divisors. Finally, we will consider if k equals 1. When we list divisors in ascending order, the products of the first and last divisor, the second and second last divisor, or the third and third last divisor equal n. So the last three divisors are n over q, n over p, and n. We want to prove that n over q does not divide the sum of the next two divisors. To simplify the expression, divide all these terms by n, and then multiply by pq. This reduces to checking if p divides q plus pq. Since p and q are distinct prime numbers, p does not divide q plus pq. This means n over q does not divide the sum of the next two divisors. Therefore, we can conclude that any composite integer with two or more prime factors does not satisfy the condition. This leads us to conclude that only composite integers with prime power satisfy the condition.